So we now consider a two charge system Q1 and Q2. The charge Q1 is fixed at the point A and the charge Q2 is moved from the point B to point C along the line ABC. The distance AB is R1 vector and the distance AC is R2. And now at some instant the charge Q2 is from the distance R from Q1. So the force from the Coulomb's law, the force is Q1 Q2 by 4 pi epsilon naught R square acting along the AB vector. So if the charge Q2 is moved by a small amount dr, so the work done dW is equals to F dot dr, that is Q1 Q2 by 4 pi epsilon naught R square dr. So the total work done to move Q2 from R1 to R2 is W is equals to integration dW, that is Q1 Q2 by 4 pi epsilon naught to integration R1 to R2 dr by R square. Okay, so this will become that Q1 Q2 by 4 pi epsilon naught into 1 by R1 by 1 by R2. So this is the work done to move the charge Q2 from R1 to R2. So if the and we know we have considered that the charge Q1 is fixed at the point A, so there is no work is done to the on the charge Q1. So the change in potential energy is U R2 minus U R1, that is equals to the minus of the work done, negative of the work done, that is Q1 Q2 by 4 pi epsilon naught 1 by R2 minus 1 by R1. So negative of this. So if the separation between the two charges are infinite, okay, so the separation between the charges are infinite, so the potential energy U should be minus of, if the R1 is infinite, then we can say that this is Q1 Q2 by 4 pi epsilon naught to 1 by R minus 1 by infinite, that is Q1 Q2 by 4 pi epsilon naught So we are talking about the potential energy, electric potential energy. So suppose the electric field at any point is E, a point R is E and the potential is V at the same point, and a test charge Q, small q is moved from the position R to R plus a small distance dr. So the force on the charge is Q into the electric field E, and the work done by the electric field, so the work done by the electric field is dW is equals to F dot dr. F dot dr. So that is equals to Q into E dot dr. So the change in potential energy, as the charge for the charge, change in potential energy is du is equals to minus dw, that is minus Q into E dot dr. E dot dr. So this is the change in potential energy. So the change in potential, we have seen in the earlier that the change in potential is nothing but the potential and change in potential energy in for unit test charge. Okay, so unit test charge. So change in potential is dV is equals to du by q. So du is minus q e dr. So du by q is equals to minus e dot dr. So dV is equals to minus e dot dr. So we can say that in vector, this is a vector scalar product. So this is minus e dr cos theta, or dV by dr is equals to minus e cos theta, or we can write minus of dV by dr is equals to e cos theta. So if this is the field, electric field, and this is the dr, and the angle between them is theta, so minus dV by dr, so this point to this point, so this is P, this is P prime. So dV by dr minus dV by dr is equals to e cos theta. So this means that the e cos theta is the component of the electric field in the direction of this dr, component of the electric field. So this is the relation between the electric potential and electric field. So this is the component of electric field in the direction of displacement. So if the displacement is along the electric field, that is this side, so then theta is equals to 0 degree. So dV by dr minus dV by dr is E. So from the definition of derivative, we know that the dV by dr, that is this is the rate of change of potential along the direction of electric field, and if the theta is 90 degree, minus dv by dr is equals to 0, because cos 90 degree is 0. So the change in potential is maximum along the electric field, along the direction of the electric field, along the displacement in the electric field, and change of potential is minimum, that is 0, along the perpendicular of the electric field. So this is the relation between electric field and electric potential. Okay, so again, if we say that the electric potential is, we see that the change in potential energy is Vb minus Va is equals to integration E dot dr if it is changing from r1 vector to our position from r1 to r2. Okay, so in Cartesian coordinate we can say the electric field as the component of the electric field Ex I hat Ey j cap and Ez k cap, and dr is equals to dx I hat dy j cap and dz k cap. So dv is equals to minus ex dx minus ey dy and minus ez dz. Okay, so if we change x to x plus dx and y and z remain same, so that is ex is equals to minus of del v del x, ey is equals to minus del v del y, and ez is equals to minus del v del z. So there, this is the partial differential equation relation between the electric field and electric potential. Okay, in the next class we will study about some charge distribution and the electric field and potential for that charge distribution. So that's all for this class. If you like my class, please like and subscribe my channel. Thank you so much.